All right, I went back and checked through the book and the example that I'd shared with you about the latent heat of vaporization, and it is based on air. So if I deducted points from your exam and that's what you'd put, come see me after class or up in my office sometime and I'll put the points back on the test for that. Now, you've still got some time until homework 5 is due. That's not due till the 19th of February, but you definitely could get started on it before then. Any announcement or schedule-related questions before we start talking about stream response? All right. Now, stream response is important to understand because it affects almost every aspect of our use of the water. Think about the ways that we use water and also the ways in which water can be not a resource but be a nuisance. The linkage between rainfall patterns and watershed response influences every aspect of that. And so one of the important ways that water as a resource is for drinking purposes. And so the availability and the quantity of water that's available is dictated by the response between rainfall and runoff response. Another aspect of that is flood prediction. And so when it rains in a watershed, there has to be some sort of a model to predict how long will it be until the stream levels or the river levels rise. And this is something that they're able to do with astonishing accuracy for the Ohio River. I don't know if you've ever watched the news or paid attention to like websites that track the water levels of the Ohio River, but you know, when it rains in Pennsylvania and Ohio, like watershed that is hundreds of miles away from here, they're able to predict within just a couple of hours when the water levels will crest in Huntington or downstream. So being able to forecast the arrival time of a flood peak is another motivation for studying stream response. But then there are also issues related to the quality of water. And when there are high water velocities, it typically will transport sediment along with the water. And so you've probably noticed that the Ohio River changes color depending on the time of year and also depending on how stormy it's been. And if there's a lot of flash flooding and high velocities, the water kind of turns very rich brown. At other times it's, I don't know what you'd call that color when it's not the rich brown. But it definitely changes. And it's not just the turbidity that is a water quality effect either. There are certain times in the spring when farmers are applying agricultural pesticides and fertilizers, where if there's a heavy rainfall after the pesticides and fertilizers have been applied, then that can get into the river. And so there's a treatment plant here in Huntington that's operated by West Virginia American Water. And in the spring, sometimes they'll have to start using powdered activated carbon to remove organic materials from the drinking water. Without that activated carbon, the pesticides like atrazine, which aren't great for your body, would remain in the water and get into the water supply. And so they have to understand basically what have the storms been like to predict and prepare for possible increases in pollution. So there's a lot of reasons why we're interested in stream response. But let's talk more about what is stream response. This is why we're interested in it. But what is stream response? Well, the simplest way to understand what stream response is the link between rainfall patterns and runoff. We've already talked about what a hydrograph is. This word hydrograph is a time-based representation of the rainfall. And it can either be expressed as depths or as intensity. And here, this is a rainfall intensity hydrograph. So if you look at what this is doing, this is showing multiple days. And so it looks like maybe each one of these bars represents the rainfall intensity during an hour. And if you know for a certain watershed what the rainfall patterns are, what you want to be able to predict is what is the stream flow rate going to be at a certain point. And so here the discharge, in terms of cubic feet per second, there could be delays between how long from when there's a rainfall to where there's runoff. There can be timing issues that we want to try and understand, and there can also be quantity issues that we want to understand. So stream response is the relationship between hydrograph and hydrograph. This is a watershed that is kind of a simplification, because we'd never see a stream with perfect, uniform, regular, straight channel like this, and likewise the contributing tributaries wouldn't necessarily be perfectly straight by this. But what this is showing is that the water gets into the stream not just from the surface, but also from the groundwater as well. And we need to be able to separate out those two effects in order to understand what is the runoff going to be, because there will be a base flow, which may be mainly groundwater, and then there will be flow on top of the base flow, which is a response to the precipitation at any given time. I'm hearing a clicking. I think it's probably somebody's mouse. I don't normally get so easily distracted, but maybe you could switch to the keypad, the touchpad, rather than the mouse clicking. Just the clicking is so noisy, it's distracting me. So we're going to talk about different flow patterns today, and how, like, the sinuosity of a stream affects the arrival time of a hydrograph at a certain location compared to if it was a straight channel. The influence of how steep the watershed is and how that affects the arrival time of a hydrograph at an outlet point. And so the basic pattern is that rain will first fall onto the ground after maybe being reduced by amount and delayed from interception. And remember that there has to be some surface wetting that's overcome before there's any flow over the surface. And there's also going to be a reduction in the amount that is a reflection of infiltration. So we've overcome the abstractions of interception, we've overcome the surface wetting, and satisfied any infiltration. And now if there's any additional precipitation excess beyond those things, then it'll start flowing over the surface. And so this is showing that water's flowing over the surface, and typically the surface flow is limited to around 300 or 400 feet. And any longer than that, the quantity of water that's pooling together is going to start flowing in a shallow, concentrated manner. And so it's not quite channelized flow, but it's flowing at a faster velocity than it would as a sheet. And this surface flow is getting into streams which gradually are getting larger because there's more of an upstream contributing area the further downstream you get, and more of these small streams contribute to large streams, and so they gradually get larger depending on how many lateral inflows there are contributing to a location that we're interested in. Now, how quickly the water is able to travel through this flow network partly depends on the type of drainage basin that we're looking at, this is related to geology. And so here in West Virginia, we mainly have watersheds in this area that are dendritic in shape, meaning if there's uniform resistance, that there isn't any kind of preferential scour or sediment being eroded, then there's going to be just a random shape, that there isn't any one direction for the stream direction since the erosion is uniform. But where there are fractures in rock, or if there are different types of soil that are layered, that there can be more regular shape patterns. So like a rectangular drainage basin could be that there's broken rock or fault lines, and so you'll notice that more of these are straight channels as compared to the dendritic network, which has more curvature, and there's not necessarily a bias to any one direction. But here in the rectangular network, it appears that there's a bias in the sideways direction, so we'd say that's maybe from the southwest towards the northeast, the flow direction is going, and then there's also a bias from the northwest towards the southeast. So it looks like there's maybe a 90-degree angle having to do with the underlying geology. So trellis patterns also, there's coastal trellis, folded trellis, where there's just a typical flow direction. So here would be a ridge line, which is maybe like a rock layer that's going in a consistent direction, and then the flow is shedding on either side of that. So the directionality of the streams depends on the geology. Stream ordering is the process of classifying how many upstream branches there are that contribute to a stream at any given location. And you could say that a first order stream is something that only has surface flow going to it, and it's not the result of any streams ahead of it. But then a second order stream is where two first order streams come together. You'll notice here it doesn't become third order until there are two second order streams joining together. And so this is just a process to understand how often there's going to be flow in the stream. A first order stream maybe would only have flow in the immediate moments surrounding a rainfall event. But then there's so little upstream area being drained that as soon as the rain is finished, a first order stream could no longer have, maybe doesn't have any more flow in it. A second order stream would have flow a little bit longer. It's likely that a third or a fourth order stream is going to have groundwater in it continuously. Even during a drought period, you could see some low flows in a fourth order stream. That's just because it's the lowest point in the watershed, then that's where the groundwater would be emerging from. So keep in mind that water flows from high elevation towards low elevation, and so the fourth order stream is at the lowest elevation in this network, and that's what's going to be driving the return of infiltrated water to the surface at those low-lying areas. A perennial stream is one that is continuously flowing. It's going to have a well-defined channel. An intermittent stream maybe only during the wet season would have flow, but continuously during the wet season. Whereas an ephemeral stream is one that only in the immediate aftermath of a storm is going to have water in it. So even during the wet, so-called wet season, ephemeral stream would be dry unless it's raining or just immediately stopped raining. Here's a picture of a perennial stream. Perennial streams are ones that are really high order, where there's a lot of upstream area and a lot of upstream channels that have joined together and are contributing to that constant flow. An intermittent stream is shown here, where there is a well-defined channel, but if we're in the dry season, then the intermittent stream may not have any flow going to it. And finally, an ephemeral stream is one that isn't necessarily very large. The channel isn't well defined. You'll notice here there's a lot of roots that are exposed, because the only time that there would be a high velocity going through there is just in the rare occasion that there's a high intensity storm. So maybe every 5 years, every 10 years, there'd be a high velocity going through an ephemeral stream. And at other periods, a 1-year storm or less often, there'd maybe only be just a small depth going through that channel. So this is showing the same watershed at different times. This is on the left showing during a dry period how deep into the watershed the channel extends, where there's actually a flowing stream is this dark black line. So you'll notice that the flowing stream part of it during a dry period doesn't extend very far compared to during and after rainfall. There would be visibly flowing water much deeper into the watershed. And then the areas of seepage are in turn, during a wet weather event, more numerous, and they're deeper into the watershed as well. So this would be like kind of a soggy area where if you walk across it, there would be groundwater emerging. And if you've ever been to Barbersville Park before, you know there's Lake William, which is near the main parking lot at Barbersville Park, and then there's a hillside by the tennis courts. If you've ever walked around on the hillside uphill of the tennis courts, it's just always soggy there. If you walk around in your shoes, they're going to get muddy and gross because there is groundwater that emerges at that location, and how much of the area is soggy varies depending on whether it's been raining recently or whether it's relatively dry, but it just happens to be where there's some preferential flow due to the probably higher hydraulic conductivity in the immediate vicinity of that hill. So seepage is what's contributing to base flow during dry periods. This is showing a watershed in Illinois. And this is a rainfall hydrograph in the top left. And so if we just look at the vertical axis, this is saying rainfall intensity in terms of inches per hour. And so there was a pulse of rain early in the storm, then it stopped. Then there's another brief period with higher intensity, and then a really high intensity period. So if you look at the rainfall hydrograph, and then you look at this hydrograph, you can see the distinct peaks that arise from the rainfall. So there was that first peak, caused this. This is the stream response. This is the rainfall. This is the runoff. So this has units of inches per hour because it's expressing the rainfall excess in terms of depth. Here on the other axis, you could also express it in terms of cubic feet per second. So you can have multiple unit systems by labeling one axis with one and the other side of the vertical axis with the other. So the thing I want to point out is that what we're looking at right here, circle the small watershed that's contributing here. It's just a drainage area of 0.2 miles squared. And that's why there's such a distinctive response. There's not much of a delay. Like if this is the same time units on the horizontal axis, like maybe these are hours, 1 hour, 2 hours, 3 hours, 4 hours, then there's just a few minutes delay from when it starts raining again and when there's a pretty high peak runoff in this small watershed where the drainage area is just 0.2 square miles. But now if we have a larger drainage area, 3.2 square miles, so in here on the picture I'm saying, what if we are expanding the portion of the watershed that's contributing? So maybe this first example, the rain just happens over a small part of the watershed, but if it rains over a larger part of the watershed, you're going to have more flow in absolute terms. So here the peak looks like 10, 11, 12, around 13 cubic feet per second. So the larger area gives us a higher peak flow rate. It's above 50 cubic feet per second. But the peaks aren't as distinctive as they were because of the travel time. That effect is called routing, and it's how long it takes the water to travel over the surface, through the small streams, which contribute to larger ones. And so the peaks become less distinctive and they're delayed more. See how the peaks are pushed to the right compared to where they were before? So a larger watershed area is going to have a less flashy response. And so a watershed is called flashy if it really is responsive in short duration and quick, high, distinct peaks compared to the rainfall hydrograph. This larger watershed is less flashy because there's just more averaging. There's more travel delay, and it could be that the rainstorm isn't having peak discharge over the entire area at the same time. And that's another thing, that if you've got a large watershed, it's unlikely that you're going to have high intensity over all of it at exactly the same time. So the storm is traveling. The periods of the highest intensity are also traveling over the watershed. But this same pattern, as we jumped from 0.2 square miles to 3.2 square miles, it continues. And so now consider a much larger section of the watershed. And now we don't see any distinct peaks at all. Once we're looking at 16.6 square miles, all of these distinct peaks are kind of muted, and the time to peak is further delayed because of the travel time that occurs. And so the basic concept is that flowing through the network attenuates the peak and delays the peak. Although the total amount is higher, so for the larger area, it's 200 CFS, it's delayed and less distinctive. So I guess I probably can't go into too much detail, but I wrote some questions on the FE exam related to this concept last weekend. So I know that they test on it because I wrote the questions. Yeah.
So when does your exam that you designed go into place? Like the next time to offer, or is that a year?
The questions that I wrote at this will begin pre-testing in July of 24. And questions before they're operationally used on the exam, they have to be pre-tested to see if they're good questions. There's like a range of difficulty and how long the question can take, and then they have another statistical parameter they call R by serial, where they want to know if people pass the exam, get your question right, that's good. You don't want to have a question that people who fail the exam can get right. So there's all these statistical parameters they look at, but they pre-test the questions before they go live. And so the questions that I wrote this past weekend will go live in January of 25. But I've been writing questions for a long time, so chances are if you take the FE exam, you may get one that I wrote. And this is an important concept, so I hope you understand it. And why? You know, understanding not only that it's a delay in time, but it's an attenuation of the height of the peak when there's a delay. And then same thing again. If the whole watershed is now contributing, it pushes the peak to the right. It reduces how quickly that peak arrives at the outlet. And so water flowing over the surface could be because it's been raining. So Hortonian overland flow, which we've talked about before the Horton method for estimating the intensity of infiltration or the depth of infiltration. So if the rainfall intensity exceeds the infiltration rate, then we'll have water flowing over the surface. And it's going to get into the stream after flowing over the surface. But water can get into the stream not only because it was raining. It could be, in the case of saturation overland flow, it could be that the groundwater table rose to the point to where now it's re-emerging as a spring at a certain location, and then it's flowing over the surface and getting into the stream after groundwater re-emerging. Or it could be return flow, which goes directly into the stream without, in some cases it's not flowing over the surface before it gets into the stream. It just emerges at the stream itself. So those are the three places that three different ways that, I guess there's four, because there's also water that falls straight onto the stream, the precipitation, but the stream area in a watershed is usually less than 1% of the watershed area. So there are a few drops of water getting into a stream that's just the precipitation falling straight onto the water. But the majority of the water in the stream is going to be stuff that either flowed over the surface, or it re-emerged due to groundwater, or it's contributing straight into the stream and hasn't previously re-emerged at the surface before getting there. So this is again showing the difference between base flow, which is the groundwater that enters the channel directly, and return flow, which is the groundwater that re-emerges, flows over the surface for a portion of the time before it gets into the stream. Any questions so far? All right. Now in wet weather, there's going to be more saturation flow because the surface water is contributing, and it can increase the rate of base flow and return flow. Just where there's more water overall, then that could increase the rate that groundwater is getting to the stream as we can break a hydrograph into components, and the rising limb of a hydrograph is generally attributed to the water that is saturated overland flow. So it's arriving very quickly, and it's more flashy and responsive to the stream. And the flow that's underneath that, the inner flow and the base flow, are the groundwater components, and they, water travels more slowly through the soil than it does over the surface, and so they arrive later and contribute a smaller percentage. And whether a hydrograph is gradual or very sharp depends on a lot of physical characteristics. And there's a quote in our book that I think is a really important quote because it helps to understand the process of a hydrograph forming. When the local abstractions have been accomplished, it's kind of an interesting word for it, accomplishing the abstractions. I think maybe I'd say satisfied, but we've overcome the interception, infiltration, surface wetting. When all that's done and said, then water begins to flow over the surface and it reaches into the channel. So the things that can affect that are the area of the watershed, how steep the channel is, the roughness of the channel. So if you have a really rocky channel, then that can delay the travel time compared to a smooth channel. The length of the stream, how closely spaced streams are, the density, the channel density means whether streams are far apart or if there's a lot of streams and so very little overland flow before it gets into a channel. And of course, whether the recent moisture conditions, if it's been rainy in the days prior to a certain event or if it's been dry. And then there can be things like the growth of vegetation or human-induced modifications to the channel that also either speeds up or slows down the rate of flow through a channel. So all these factors can play a role in translating between the hyetograph and the hydrograph. So slope, this comparison is showing that if you have a relatively shallow slope on a hillside, if the water's flowing over the surface or if it's flowing in a stream, the steeper slope is going to have a quicker time to peak and a higher peak compared to a gentler slope. If you have water flowing over a surface that's relatively smooth, then that would cause a quick arrival of the peak compared to a rougher surface, which is going to have a higher Manning's N, which reduces the flow velocity as the water's going through the channel. So it'll arrive later, and because it arrives later, the channel, the peak is lower. So this is the same volume of water, but delaying it necessarily causes the peak to be lower. Just think about if you're smashing this, it's the same area under the curve, but if you delay it, then that has to make the peak lower as well. So it's slowing down the velocity, and more of the water is going to be retained earlier on. So it drains for longer if it's a more rough channel. You'll notice this is kind of showing two extremes. You can think of the storage as puddles along the way. If there's a lot of small puddles along the way, or sometimes these can be engineered that intentionally this pool would have to be filled up before water goes to the next pool, which is filled up, flowing down to the next one. Whereas if there's little storage along the way, it just arrives more quickly, and so the increase in storage quantity in the channel or in the watershed is going to delay and reduce the peak. Drainage density, let me show you a sketch. Well, I don't have a dry erase marker with me. Drainage density, I can go back to one of these prior slides, and so just imagine, what if there were half as many streams in this picture? So if water had to travel over the surface for a longer time before it got into a stream, then that's going to have a more of a delay than if you have a high density of streams, then less of the time is flowing over the surface, which is relatively slow. When the water gets into the channel, then the water is able to move at a high velocity. But if you've got a high density of streams, then there's more channel flow, less surface flow, so faster arrival times compared to a low density of streams. And then the last one, channel length being longer, is going to force the water to kind of spread out. And think about if you took a glass of water and you pour it in a rain gutter. So if you have a long rain gutter and you pour it in, it's going to arrive at the outlet of the rain gutter, not in the same duration that you poured out the glass. Like if you pour the glass of water over the course of 2 seconds at one end, then the water's traveling through the rain gutter and it finally comes out, it's going to be filling, if you put the glass now at the outlet of the rain gutter, it's going to take more than 2 seconds to fill that glass up, because it has to, its movement over the surface is being slowed down by friction, and it's spreading out and delayed in the transit between the 2 points. And so that stream routing delays the peak and reduces its intensity. Any question about either of these? Just a second. Okay. Here is showing a hydrograph up above and a hydrograph beneath it. And this is showing if you have a storm, you could have the same overall depth of precipitation, but if it is front-loaded in the storm, then the hydrograph will arrive earlier compared to if the storm is just a little bit at first, but then later in time, then the hydrograph would arrive later. So temporal distribution is a factor that can influence what the hydrograph stream response looks like. So the same depth, but just different timing could have an influence. And then the location of the storm and the scale of it over the watershed. So this is showing, for example, if it's just raining in some outer reach of the watershed rather than the whole thing all at once, think about how long it takes for the water to travel through this network before it finally arrives at the outlet. So storm A is less in height because it's not the entire watershed area that's contributing, but it's also delayed because of the travel time from this farther reach down to the outlet compared to storm B. And then the storm movement is suggesting, what if we had a storm that started raining at A and then the clouds were moving towards B? So if the flow was originally close to the outlet, then it would show a quicker arrival time than if it started at this far area and it was traveling towards A. So the delay is because it started at this further location, but notice that it's also higher. If it's the same storm, but it's traveling in the direction of the outlet, the peak could be higher because the rainfall is arriving at A at the same time as the water is arriving at A that was previously falling at B. So they're both kind of converging on location A at the same time. The old precipitation, which has traveled through the network, and the more recent precipitation, which is falling on A at that very moment. So, looking at gauge data, if you go and get the Huntington Tri-State Airport, you can find out in a 24-hour period how much precipitation there was. But just because 2 days have the same precipitation depth doesn't mean that you're going to see the same runoff hydrograph behavior. If you have a 3-inch storm on one day and a 3-inch storm on a different day, you may also need to know what direction the precipitation occurred or over what section of the watershed it was happening, because there's a lot of variability that can arise because of the storm direction. So rainfall excess is the rainfall that isn't retained on the surface nor infiltrated into the soil. So retained at the surface would be surface wetting and interception, not infiltrated into the soil. So it's the leftover. And if we put a rainfall hydrograph, and this is the declining potential rate of infiltration curve. So this curve could be generated either from the Horton method or green amped, but there's some way for us to figure out how much water is going to be absorbed by the soil. So the hydrograph portion that is above the infiltration curve is the rainfall excess. So we're saying total rainfall is infiltration plus rainfall excess. And so with this curve, what we could do is know for every time step how much rainfall excess there is. And then we could put that into a model that relates a certain amount of rainfall excess to a certain amount of runoff. And infiltration, remember, is decreasing over time because the soil is becoming more saturated, the suction head is decreasing, and we're just approaching that gravity flow rate. So this declining rate of infiltration means that as a storm goes on, a greater portion of it may be rainfall in excess than at the beginning of a storm. You may have almost all or all of the precipitation going to satisfy the infiltration. The hydrograph is usually represented as a bar, a series of bars, whereas a hydrograph is a continuous line or a curve that's showing either the depth or the velocity or the flow rate versus time. So this is a conceptual figure here that allows us to translate a rainfall hydrograph into a hydrograph. So we start off by looking at the rainfall rate versus time and subtracting out the infiltration rate from that to find out what depth or rate of rainfall excess there is. And now translating a rainfall depth into a runoff amount, there are several different ways we're going to do that. We'll learn about them next week. There are unit hydrographs, which are specific to a watershed, and it's basically where you've done a previous analysis and you found out how much runoff would there be at any given time. Like, what does the hydrograph look like for a unit of rainfall excess? And so that could be an inch of rainfall excess. How much flow rate is there going to be at that watershed? Most watersheds don't actually have direct physical measurements, though, so we have to use synthetic methods to translate rainfall excess into runoff. And there's a lot of physical parameters like the watershed area, its slope, the soil characteristics, and the land use. A lot of physical characteristics like that that can inform what the shape of the hydrograph looks like. And then this last step is just adding the groundwater on top of it, the base flow that we know would be present even if there wasn't a storm event. And so the overall total hydrograph would be the combination of the base flow and the runoff, which occurs because of rainfall excess. Okay, that is all I have for you today. Well, look at that, 1:39. I'm letting you out 11 minutes early, so keep that in mind for those times when I hold you a little bit late in the future, because they will happen inevitably. If you were any of the students who I deducted points for problem 3 on the exam, let me know. It doesn't necessarily have to be now if you don't have your exam paper with you, but stop by sometime and I'll get it sorted out. See you on Monday.